Hello, welcome to another session to IFT ZK call. Today, Marvin presents the Fiat-Shamir heuristic. Recently, I discovered an attack on the Fiat-Shamir non-interactive version of GKR. Stage is yours, Marvin.
Okay, so to begin, we're going to actually talk about two different attacks on Fiat-Shamir to make this as accessible to a wide audience. So the first thing I want to talk about today is kind of like what is Fiat-Shamir and the normal, in quotes, normal, the standard way that Fiat-Shamir is usually used inappropriately. So that will be the weak Fiat-Shamir attack that, that's been very popular to talk about for the last about 3 years. And then after that, I'm going to talk about the recent attack that Igor mentioned that involves GKR. And in my corner of the world, I haven't seen much people talking about it, but it looks like it should be a very big deal on the vulnerability. And that's going to be what we will conclude talking about. But let's begin. Now, to begin talking about, a Fiat-Shamir, weak Fiat-Shamir attack, we really need to have our standard example of protocols, which is the Schnorr protocol. So with the Schnorr protocol, we just have the prover and the verifier, in this case, exchanging messages. And what the prover wants to do is prove to the verifier that they know the discrete log of gamma, where gamma is equal to g to the x. So g is known up front by both parties, and gamma is known by both parties, because that's what the prover is claiming to know, is that they know this x. Now, obviously, the prover could just provide x to the verifier, but that would be no fun, especially since the Schnorr Schnorr protocol was originally a signature protocol. Kind of gave away the punchline in that sentence early on. But, so we don't want to hand over x. Instead, we're going to, perform the following protocol, where the prover will compute this alpha value, which is a group element, and so they'll know this t value, but the t value they'll keep secret, and they'll send alpha over to the verifier, and the verifier is going to send this random c value. And it's important that we do this in this order, so that c is chosen independently and random compared to alpha. If the verifier sends C before alpha is selected, then obviously we can kind of manipulate our choice. And then based on that, we are going to have the prover compute just what this response Z, which is T plus XC, and send that over to the verifier. Checking a nice identity, the verifier will be able to conclude whether they believe that the prover knows X. And that's, just kind of fiddling with these exponents, you see immediately that if gamma is g to the x, this will work out. Now, this is a very nice protocol. And with this protocol, we have a transcript. And the transcript is given by alpha CZ. And this is just the order that we exchange the messages. And this is the transcript, if you want to be completely pedantic, the transcript of the interactive protocol. The difference between an interactive protocol and non-interactive protocol is that this required direct communication with the verifier. We want to remove that communication so that any verifying party can check the proof. Now, to do that, we have to get rid of the C. C has to be, well, not get rid of the C, but the C needs to be computed by the prover. But we need to do it in such a way that we have assurances that it is random and that it's independently selected based on alpha. And that's where the Fiat-Shamir transformation comes into play. And all it does is basically goes, okay, well, we're going to prove, we're going to take a modification of our proof system, and all the challenges are going to be evaluated using a hash function based on all the public values. And for the strong version, we really have to include the public parameters. The public parameters is what really messes people up. And we're going to see why this is a big deal to include the public parameters, because if you don't, then that's going to be bad. But let's take a step back and kind of mention what the public parameters for Schnorr is. The public parameters for Schnorr is going to be this G value, and we really need to include gamma. So you really should include all the public values, being the statement, any messages that's exchanged by the prover being alpha, and gamma is the statement, so we should include that as well. So we need to include all three. Now, let's see what happens if we only include alpha. So we're going to, proceed essentially with the idea of Schnorr in our head, that we're trying to prove gamma is equal to g to the x without revealing what x is. And now the prover is going to compute the challenge, but just with alpha. So this is weak Fiat-Shamir, where we do not require the public inputs to be, the public parameters and inputs to be included. So notice from this, gamma and g really are not fixed by C. And this is going to be a problem, because that means that the malicious prover can then define her claim gamma after having figured out C. Now, not having G in here is not as big of a deal in quotes at the moment, if we assume that, we're just using like a G that the verifier and the prover know, like that's just committed to on like a blockchain. Like if we assume that the generator G is known to all parties and that cannot be affected, way before the prover decides to be malicious, we don't really need G there because it's fixed. Gamma we do need, but if we were setting up a random messaging, we would want G in there. But so given this, a malicious prover can define her claim gamma after C. That's the important part. And what would happen is alpha is selected, and notice that we don't really need to know what T is. So we could really just take any alpha in the group, select any natural number, well, any number in ZP, and the only thing that we have to worry about as a malicious prover is that the verifier is going to compute this C. They know how to compute C is H alpha. But given this, we can forge this gamma maliciously in this, using this gamma and publishing it. This ensures that the verifier, any verifier, will always accept that Schnorr proof for gamma. So that's a problem. Now, if we do this properly with strong Fiat-Shamir, then what's going to happen is we're going to include both G and gamma. And once we've included both G and gamma into our hash, this will prevent any cheating, because the hash function should be collision resistant, at least taking a cryptographic hash function. So that's going to prevent any kind of working backwards that we were able to do with weak Fiat-Shamir. Okay, so this is a very kind of, if you're looking at this, you go, okay, well, this seems kind of obvious, and this certainly was in the literature. I know it was certainly the weak Fiat-Shamir and strong Fiat-Shamir definition I saw was certainly 2012, I think, and I'm sure people knew, experts knew, we'll phrase it that way, of this being a problem early on, but just because experts are aware of things does not mean it's trickled out in practice to everybody in the field or engineers. And as a result, we see in 2022, Trailbits published a bunch of blogs basically outlining instances of weak Fiat-Shamir. They called this particular vulnerability Frozen Heart, which sounds way cooler than just saying, weak Fiat-Shamir. But they found this instance in multiple places. They found it in implementations of Plonk. They found it in SnarkPack, Bulletproofs. And it's kind of permutates in a lot of places. And one of their conclusions that they made is that this issue often occurs because when people wrote papers, they would just say, oh, well, we can make this. They would present a interactive protocol in full detail and go, okay, well, we can make this non-interactive by applying Fiat-Shamir. So you'd have a section, of a very, very short section of 2 sentences, where it would just say, we can make the protocol above using Fiat-Shamir, and that would be it. But no explanation about, hey, make sure you use your public parameters so that this is secure. But because of that, you could forge false proofs because of weak Fiat-Shamir. Open Zeppelin also had a paper, I think last year, called The Last Challenge Attack, which is a attack on Plonk that basically assumes weak Fiat-Shamir as well is being used. So there's been a lot of interest in this. Any questions on the weak Fiat-Shamir side?
I think there's none.
Okay.
The chat is clear. Yeah.
Okay. Cool.
One question regarding the terminology. A transcript is typically refers to the ordered tuple of all prover stages, and if so, I guess that if we talk about Schnorr protocol, then when prover claims something, for example, he claims that gamma is calculated all in one, which is a part of this claim, is also applicable.
Usually, okay, so I see what you mean. Thanks for reminding me. Before I answer your question, I will point out one thing that I kind of hinted at earlier on, but I didn't explicitly say. When we were on the slide originally, I did say that this was the interactive version of the transcript. When you do a non-interactive protocol, you would just go ahead and omit C. So for the non-interactive transcript, it would just be alpha Z, and that's because the verifying party can compute C. Now, to your question is, well, gamma seems like it should be part of the transcript. And this, I think I've seen a paper where gamma's been included in the transcript before, but it's not necessary, because usually the idea is that the transcript proves your statement witness pair. So you would just go, okay, this transcript proves this statement, and that, so you kind of have those as separate notations where you have an order pair that's the statement and the witness, and then you have the vector that is the transcript.
Actually, if we're talking about a transcript, then a transcript is it includes everything about prover says, including the statement, including the messages to prove, and that's all to make sure that it's true. Ask now ChatGPT questions. Transcript in 5 cents for the order messages. Yes. A message, for example, means if the proof why is to the x, then y is of the transcript.
You cut out partially, but like I said, the form that I traditionally have seen it in papers usually keeps the statement witness separate from the transcript. That's not to say that people don't do it other ways. This is just the way that I'm more accustomed of seeing it. But we both agree that essentially everything in the transcript would be include. So the difference in terms of how we would phrase Fiat-Shamir would be, you would say everything in your transcript up to that point is included, and I would just go with the statement and the transcript would need to be included. So,
yes,
but we would still mean the same thing.
From practical point of view, we are talking about the same thing. I mean, the same way in which the Fiat-Shamir should be implemented. I just mean that it can be more beneficial to include in the definition of.
Oh, I see what you mean. I think this gets a little unfortunate. I think that version gets a little weird if you're talking about the rewinding lemmas or the forking lemmas, where you're only focused on the transcript. An array of transcripts or a graph of transcripts. So it might be a little, because they all have the same root statement. So that might get a little weird if you're looking at the forking lemma with your version.
What forking? What could you repeat?
The forking lemma would with your definition, the forking lemma would become a little awkward, because the forking lemma is basically a check for soundness. And what you do is you rewind at each challenge, because if you're with the Schnorr protocol, if I rewind from here and I offer another challenge C prime, I'm able to extract the witness. So that gives you a graph, and what happens is these parts would have it would just look a little strange essentially if you included, at least in my brain, it would look a little strange. But the forking lemma is just basically a claim on soundness based on rewinding and issuing new challenges. But it deals with an array of transcripts that can be sorted into a graph, into a network, essentially.
Mm-hmm. Okay, I'll take a look at this lemma. Thanks.
The simple version of that lemma is the rewinding lemma from Dan Bonet. I think Dan Bonet approved it. But yeah, but that's a good lemma. All right, other questions? Okay.
Actually, I think no.
Okay, fantastic. Okay, so like I said, the weak Fiat-Shamir, it was a known attack. It was something that's it was unfortunate when it occurs, but with the weak Fiat-Shamir, you go, okay, great. All we have to do is be explicit, make sure engineers are aware of the issue, and that they don't commit, this horrible sin and make our systems vulnerable. That is an easy fix. You make sure everybody's on the same page and that they are, implementing it correctly. Great. And then I think last month or the month before, because time is weird, especially at the beginning of a new month. A paper came out, and it kind of is slightly depressing. And it's also exciting because, that means that there's new research being done on it, is that we have this new attack, which uses GKR, but not quite fully. But the more important part is it's assuming that we have strong Fiat-Shamir being used. And that's the terrifying thing. One bit of trivia that I thought was interesting that I saw in a recent video posted on this. I think the people who post that one is proof in the pudding, but they beat us by like a week to having a presentation on this. But they mentioned that Rothblum, and I apologize if mispronounced their name. So I see this name and I think, oh, this is one of the authors of GKR, because that was part of. Turns out that this attack is actually written by their brother. So we have a Rothblum who wrote GKR, and his brother found an attack using GKR. So sibling rivalry at its best? Question of the day. So I thought that was interesting and hilarious when I heard it. So anyway, now there's a few things that are really interesting though about this attack. One, a malicious prover only has to be dishonest for the beginning of the attack, and the rest of it they can behave completely honestly, and it will work. Which is kind of terrifying that there's like one step essentially where they can just wreck everything. But before we get into that, let's kind of mention why this is possible. Why is this possible on newer protocol systems potentially? And that's because the old ones used to be like just signature proofs and identity proofs, just very simple. But now we're doing general purpose computations with our circuits, and that opens things up a lot. Additionally, GKR goes further with these general purpose computations, and it doesn't even require a commitment to the computational trace, which is one of the benefits of GKR. So that's problematic. And the other thing that they do is they allow for the witness they assume that the witness is large enough to contain either a commitment or the hash value. Basically, they want the witness to be large enough to contain the digest of the circuit. And that's surprisingly not as restrictive as you might think. So that could be a problem. I'm interested in seeing some analysis on how vital that would be, but it looked pretty bad. So their paper outlines 3 different attacks, and each attack gets worse and worse. We're going to talk about the first attack in detail because, one, this is not aimed to be too technical, but technical enough. And the first attack really gives you an idea of what they're doing. The other 2 attacks take that first attack's idea and extends it. So we're going to see what we mean. So the first attack is going to work with this circuit. So they built a specific circuit to show that they can do some, use strong Fiat-Shamir and just wreck everything. And what they're going to do is with this circuit, they're going to just go, okay, well, our witness to the circuit, and the circuit does not have any public inputs. It only has a witness. And we're going to assume that witness is actually just the digest of the circuit. Okay, fair enough. And what we're going to do is we're going to compute this alpha value to be the commitment of our witness. So we have a commitment of the circuits digest. And from there, we're going to go, okay, we're going to compute our challenge. So we can view this as a challenge where it's gamma, and we're going to have our circuit digest. The circuit digest is assumed to be our public parameter here, if we're thinking about this as strong Fiat-Shamir. Our claimed output, where we're going to claim our output is 0, 0, and that will make sense in a second. And our first value we gave them our commitment to our witness alpha. Okay. And at the end of this, we're going to output, so our circuit's going to output gamma and then gamma minus 1. But our claimed output was 0, 0. That's not possible. Our claimed output doesn't even make sense for this circuit. Now, you can actually make 0, 0 be something different, but for multilinear extensions, it's just going to be easier to do 0, 0. And, but it will still work if you alter things a bit. So, okay, so immediately off the back, if we're analyzing this, we can see something bad's going to potentially happen. Well, what happens now is you go, okay, if I take a multilinear extension of the proper output, of what the proper output should be, we have gamma, and we have an array, just to make things make sense. We have an array of gamma minus 1. So if we take this array and we compute the multilinear extension of this, then when we plug in, we want a linear function that will give us gamma when we plug in 0, since that's the 0 entry, and give us gamma minus 1 when we plug in 1. Oh, well, that does exactly what we want. Great. So we have our multilinear extension. And now, if we take the multilinear extension of our claimed output, well, 0, 0 is just going to give us 0. So notice that both of these agree when we compute our claimed, our strong Fiat-Shamir challenge, R. But inside the circuit, we computed gamma as this, our output. So what happens is, within our circuit, we compute our challenge that happens to also be part of our output. So we're assuming our circuit is big enough that we can compute the hash in this commitment. So yeah, there should be a hash. I apologize for that. I just noticed that was missing. But so we're assuming it's large enough to do that. But once we have that done, the rest of this proof, the GKR, the malicious prover can behave honestly. And that will be sufficient for it. Because again, GKR does not require us to check this computational trace, commit to our computational trace or prove anything about it. And we're assuming that the circuit is big enough that you can compute these hashes. And this provides us a one step where we were able to lie about our input, both our multilinear extensions, the proper one F and the claimed one G, match at the one point that the verifier cares about, being R, that we compute in the same way we computed gamma. And after that we're screwed, because GKR can resume normally and it will break. Now, you're probably looking at this going, okay, well, that sucks, but that's a very contrived example. And yeah, it's a contrived example. However, random blank slide. But it does work on more elaborate circuits. The second example they give is a if-then circuit, which Since we have a few minutes, well, I'll pull up if people are interested. But it works on if-then circuit, and then it also works on a universal GKR circuit as well. And that is where the power really lies. Like I said, if you understand the first example, you can work through and get the other two, because it's really just kind of applying the same general idea to more elaborate examples. But the really dangerous part is that they don't even require you to have the hash function included in the circuit. They can also, you could have an additive homomorphic commitment, and that can also be exploited. In fact, they prove that for any additively homomorphic commitments, the GKR protocol for a universal GKR circuit of large enough depth is unsound, which means it's open to the strong Fiat-Shamir attack. Now, additively homomorphic refers to both the versions that we all think about in terms of elliptic curve commitments or Pedersen commitment. It also refers to some of the newer lattice-based ones that are kind of, additively homomorphic as well. This is not known to be a problem for FRI-based protocols. However, because the FRI-based protocols recently have been using batching methods, which use commitments and other things to kind of compress them together, this same attack can be used there. So this seems like it should be a much, much bigger deal than I'm currently seeing. But yeah, so things that we need to, as researchers, take into account. In terms of engineers, like I said, the weak Fiat-Shamir is the one for that, but this kind of calls into question some of the security assumptions that people have been making in the last maybe probably longer than 8 years, but I'm going to say 8 years just because Bulletproofs was 2017. But certainly a big deal. GKR was a little bit earlier. Anyway, so that's all I have. I'm happy to answer questions, making sure there wasn't another hidden slide.
Thank you, Marvin. Yeah.
Returning to the floor.
What was that?
Do you have any question?
Yes. Yes, you.
Yes.
Okay. So returning to the foreign lemma, you mean that implies how late?
You're breaking up a lot. Can you repeat that or type that?
For the let me means in the text include.
You're breaking up a lot. I'm only catching every fifth word, I think.
Let me reconnect.
Okay.
Okay. Meanwhile, as far as I understand, the only the Fiat-Shamir of the GKR is affected this attacks, right? Not the general Fiat-Shamir.
Well, that's not. So what this raises is concerns that the general usage of strong Fiat-Shamir might have issues. If you have the computational trace that they mentioned, maybe that's enough to keep you secure. But right now, it's unclear whether this attack Well, you have to keep. Let me phrase it this way: the Fiat-Shamir transformation is usually referred to as a heuristic because it's not really proven. Because if your hash function's bad, then it can be vulnerable and stuff like that. So, what this indicates is that there are instances where the heuristic fails. So it's the question though is, are there other environments where it fails? If you include the computational trace, like we think about with RISC-0, then you might be okay. But you also have to keep in mind there are some ZKVMs that use GKR, I believe, for the compression. And there's also the fact that they mentioned that FRI-based protocols that use batching could be open to the same attack. They kind of mentioned this offhand. I haven't thought about too much yet, but that could be a problem. I don't think anybody at IFT uses FRI-based. No, that was dumb. Obviously, Codex does. I always forget that Ponky 2 uses FRI for some reason. I don't know why. But
okay, thank you. Sorry, Alexei. I just I just thought that you have more time to reconnect. I just wanted to ask a very big question. Yeah, go ahead, Alexei.
Can you hear me now?
Fantastic. Yes.
Okay. So the question is regarding the forking lemma. You mean that including the statement into the transcript sounds weird in the context of the forking lemma? I guess you mean the following thing, that in the context of forking lemma, a prover can produce different transcripts, different messages, while if you include a statement into the transcript, then it cannot hold true for the statement because the statement is a constant, and thus forking in terms of fork it contradicts the main principle of forking lemma, in which implies that prover free to choose any part of transcript, correct? Or
the verifier can rewind to any part of the transcript. But that's only based on where the challenges are. So I need to probably pull up the visual aid. Give me 1 second. But yeah, the forking lemma allows you to rewind to the verifier to rewind to issue fresh challenges, and that allows for essentially a chance to reconstruct a different proof. I just need to a diagram essentially, so that's why this is being pulled up. Not that any of this matters. Yes. In terms of whether anybody should read my dissertation, I go with probably not, but it exists. Now, so the rewind. Oh, this is actually perfect. Sorry. Yeah. So right here is essentially a tree that is formed from the rewinding lemma, or the forking lemma. And what happens is from the statement, you from the public parameter initial statement, you kind of work your way down through different challenges to different paths of your statement. and that gives you, and each of these paths on this tree is going to be a transcript for the overall argument. Now, the reason that it's not mathematically wrong for you to say that the transcript includes the public statement, but it's a little awkward because usually you want to kind of look at just the vector and then you have the root separately. But it's one of those things where I think the term is not necessarily. I think there's room that it could be defined one way or the other as long as you're clear.
S0, S1, and S2 are different parts of some position.
P1, P2, what?
S1, S0, S1.
Yeah, so these are different because what happens is this is a more general idea of protocols where it's a reduction. But so basically at each step I'm considering a sub protocol, essentially a subroutine. So this overall, each interactive protocol can be viewed as a reduction. The only difference is that a protocol should end in accept or reject, and here I'm ending at a statement. But that's not important.
Or maybe in this case, different indices near PP. Seems that this describes the possible outcomes of cut of Fiat-Shamirs for state.
You're cutting out again. Can you type your question?
This light.
Yeah, it's breaking for two, I think.
Yeah, I don't know what you're saying anymore.
Yeah, if you have open VPN or something, just you know.
Like
What's now?
Okay, you're fine now.
Okay, I can understand that this pure situation all with an interjection. And
Yeah, you're breaking up again. I'm sorry.
Let while internet. Okay. Let me.
It's weird because like you get a moment where it's fine. While Alexia, while you fix this, Omir, did you have any questions?
Yeah, actually, like it's a very nice presentation. Thanks for the opportunity. Just curious about like what are the practical applications of this attack scenario? The only attack scenario I know that might affect, for example, Bitcoin network is nonce reuse.
Okay, yeah, absolutely. So with the weak Fiat-Shamir, what can happen is if you so in the instances that they mentioned, like say like I apologize because I don't remember some of the instances in which these are explicitly used. However, I'm going to pick on bulletproofs because I know who used that and what they used it for, which might be bad later. But I don't know. I don't think Monero had this issue, but Monero used bulletproofs at one point for a range proof in their currency. Now, if they had the weak Fiat-Shamir issue, so not saying they did, I have no idea. I'm saying if they did, and this was known, what you could do is you could forge a proof of value essentially that you didn't have. So you'd be able to essentially lie. And that's kind of the danger for like cryptocurrencies. But you're able to falsify your records. Now with the new attack, this one's a little weird because I don't know of any cryptocurrencies that use GKR, but I think, and you can correct me, but I think Nexus might use GKR in their ZKVM. And certainly there's a recent one that proposed using GKR called Sino. And what that would do is that you would be able to essentially falsify a proof of execution on the ZKVM side. And depending on where that ZKVM is used, like if it's embedded, say, with Ethereum, you would be able to falsify a ZKVM proof, which is then accepted by the blockchain, and that could do untold damage depending on what the smart contract does. Like, if it's a smart contract that is involved with a DAO and allows for off-chain ZKVM, proofs, you could drain the DAO again. I will say with the GKR ones, the thing that might protect some of those is that you might have to make a more circuit specific one. Also, maybe the circuits aren't deep enough to cause the damage. But with weak Fiat-Shamir, you can forge whatever proof you essentially, whatever proof you want. With the new attack, it's kind of uncertain how bad, but you can certainly forge whatever proof you'd like. It's just, are systems vulnerable to it and provide enough circuit size that this is a problem? I can't really answer that, unfortunately.
I quickly searched about some POC or something, but I couldn't find from GitHub.
Yeah, for some reason I have GKR in my head for Nexus, but that doesn't make sense because they use Spartan and they use Grot 16, so I might just be misthinking. But I do know Sino is a GKR ZKVM that was a joint effort between Scroll and a university, I believe. Anyway, did that kind of answer your question, hopefully?
Yeah, absolutely. Thanks for the insights.
Okay. Alexei, let's see if you're...
Okay, can you hear me now? I'm using the mobile internet.
Yes, I currently can hear you. Hopefully we can hear you in like 5 seconds.
Yes. So, did I correctly understood that the tree on the picture was representing possible outcomes of situation where prover and verifier interact to prove several different statements? The first one
it's the same. It's all trying to prove this original statement.
And what is S0 and S1?
S0 is the original statement, and PP0 is the original public parameters. You can kind of ignore these subscripts.
And S1, S2, S.
Those are, like I said, this is for a reduction. So when you consider reduction, you're actually considering it going into different witness statement spaces. So that's what that is. But that's not important for interactive protocols. It's just this was the diagram I knew where it was.
Okay. So while I was,
in fact, I can just do this. Here you go. This is probably better because you have your original statement, and these are just where the prover would output another value. So for like Shamir, this would be where alpha is, and then you would get another challenge that would give you each branch.
So, by the way, regarding I asked ChatGPT, is considered a statement proved as part of a transcript inconsistent with terminology of the forking lemma, and he has some with conclusion. In short, considering the statement being proven as a part of transcript, being proven as a part of transcript is not inconsistent with the forking lemma, as long as we recognize that the forking lemma is considered is concerned with the sequences of provers' messages, commitments, challenges, and responses, and not with the initial statement itself. So
Yes.
actually, we can taking into account all this, perhaps it would reasonable to formulate the Fiat-Shamir protocol in the following way: that the data to be hashed is all public data, which includes the statement, and we can consider so-called variable provers messages, and the variable provers messages are their tuple is the one which the forking lemma is applied.
Well, with Fiat-Shamir, you wouldn't even consider the forking lemma because Fiat-Shamir guarantees that you have just one path.
No, no. Of course, in terms of Fiat-Shamir, of course, it's deterministic. I mean, in terms of interactive protocol, yes. To make correctly, all those things which I have told, it was not regarding the Fiat-Shamir transformation, but to the interactive protocol. But to interactive protocol which precedes this transformation, something like this.
So, I mean, the tricky thing you would run into is trying to redefine essentially a definition that's 30, 40 years old at this point would be tricky. With like strong Fiat-Shamir, I think that was from 2012, so it's at least relatively recent. But that was probably more of a pointing out an issue that could occur if it's just vaguely public values.
Actually, sufficient to have the term strong Fiat-Shamir transformation, and it closes the question about ambiguity between including statement, non-including statement, and so on. Correct?
Can you repeat that?
So, having the term strong Fiat-Shamir transformation is completely sufficient to eliminate the ambiguity between including and not including.
It is, however, people usually just say Fiat-Shamir, and that's the problem. So you also have to keep in mind that people are going back and reading older papers that were not necessarily well written. So, well, it's not so much not well written, but weren't as careful. We'll phrase it that way, and that can induce other issues. So there's definitely been a concerted effort in the last few years to make sure engineers and everybody in the space know to use strong Fiat-Shamir.
So talk about documentation beneficial to.
I think it breaks again. Do you mind to close the camera? Maybe it helps to enhance the.
Okay, let me stop the video. Perhaps it would help.
Maybe.
Okay, so how do you think? Is it important to write not just Fiat-Shamir transformation, but strong Fiat-Shamir transformation? For example, when we describe some proof or something like this to avoid ambiguity.
I think you should always describe strong Fiat-Shamir. The only instance that I've ever seen defend using a weak Fiat-Shamir is in the instances of signature schemes where things are small enough that it's a non-issue. But based on the, I think the complexity to compute strong Fiat-Shamir versus weak Fiat-Shamir is neglectable. So you might as well just always use strong. And
Of course, I mean,
confusion.
I'm asking not about some practical point of view. From practical point of view, of course, it's always correct to perform to implement some Shamir transformation. I just mean about asking about terminology. Is it to use Fiat transformation, not just Fiat-Shamir, for example, some specification or some proven system, because if we talk just Fiat-Shamir transformation, right, about just Fiat-Shamir transformation, does it by default mean to be strong or weak, or it's just some gray zone, and we should explicitly say that we are talking about strong Fiat-Shamir transformation?
I think it's okay. Yeah. So there's two ways that you can handle this. One is if you're writing a paper yourself, you can write the Fiat-Shamir transformation definition as I have it here and just omit the word strong. And you just go, hey, this is the only version, and just not even worry about it. But like I said, you kind of do a disservice to some extent when you do that, because not everybody reads every part of the paper. They might skim through and go, oh, you're using Fiat-Shamir. I know Fiat-Shamir. And if they don't, if they know it's the weak version, that's a bad thing. But if you write strong, it might make them actually go, wait, I don't know what strong Fiat-Shamir is. And then they take a glance and they go, oh, okay. So if you're writing like a blog, it's probably better to say strong Fiat-Shamir and just emphasize that you include the public parameters. But in terms of a theoretical standpoint, is there any reason not to just rename Fiat-Shamir, strong Fiat-Shamir, to be Fiat-Shamir? There is no good reason not to do that, except for the fact that there's so much literature out there that renaming things would be bad and confusing.
Okay, thanks for interesting information, because actually what I was the implementations which I have seen, for example, if I'm not mistaken, with Halo 2, the version used by privacy scan exploration, as far as I remember, if I'm not mistaken, this implementation was based on strong Fiat-Shamir transformation, and for this reason I thought that actually all Fiat-Shamir transformations are something which you call here strong Fiat-Shamir transformation. Now I know that it's worth it to use the additional word strong.
Yes. In all implementations that you find should be strong. If you don't see it as strong, that's not reassuring, unless it's like I said, digital signature, where that is. I've seen arguments saying like this is fine, but yeah, Zcash would definitely have Fiat-Shamir correctly implemented. But yes, the careful phrasing of strong is important.
Thank you.
Yeah, thank you, Marvin. I think there is no further question, and we can wrap up.
Great.
Thank you once again, and thank you for audience. And these notes will be on the WAC forum, right?
Yes, I will
Okay,
be posting the notes
yeah.
shortly.
So
And everybody
we
can join the conversation.
So we can continue the WAC forum
Yes.
for the further discussion. Thank you. Bye bye.
Goodbye.